All right, so a few things first. Somehow we ended up not having a quiz this week. Anyway, the material was kind of fuzzy, so it's hard to ask questions out of that. I'm going to have much stronger material, so let's just skip the other quiz. I'm going to have a nice quiz on fault tolerance this week because I'm going to teach some material that's much more interesting. Sorry about that. The other thing is the project, right? So in case you're wondering, part one, I already said this to people in class, but part one is a little bit simpler, even though you still want to do a very good job on that. It's a little bit simpler to allow you to start very early on part two. Right? Now, when it comes to part two, sky's the limit with what you can show me. Right? What I would like you to do is ask some hard questions about what would have helped you with the other projects. Right? So capitalize on the frustrations, on the experience, on whatever else about the other projects, and also try to capitalize on other skills you have. I mean, this is your chance to put together a lot of the things you know, right? So, I mean, you're extremely good with web development, do a nice web interface. You're good with Windows programming, do Windows programming. You want to design nice languages in which you can express those constraints so you can find things. Hey, do that. Right? Anything you learn anywhere in computer science can be used here. I mean, it's really something that has no limit with what you do. Now, the question always is, what's the minimum I need to do to get full grade? Well, I mean, I don't want to specify very precisely what it is. You can pass by me some of the ideas, right? But try not to shoot for the minimum. Try to shoot for something that's nice, useful, that you can show to other people, right? I would even encourage you, if your project really takes off and it's very nice, to even open source your project and make it available to the community. And as long as you don't depend too much on Scala for the whatever are you going to do, visualization or whatnot, in terms of what's the source language, you can actually use a tool like this for almost anything. As long as you produce, for example, logs in a universal enough format. It's hard not to produce them in a universal format, right? Because even for Scala, I need to serialize them to something, right? As long as you don't serialize them to some binaries that only are good for Java or Scala, you're fine. And you have no reason to do so. For example, one idea is to produce logs directly in JSON or some other universal, easy-to-read format, for example, YAML. So these are ideas, right? So the log can be in JSON, for example. I mean, I'm not going to force you to do this, but I'm just saying if you do this, then a lot of other tools can be used to do part of what's needed for the project. JSON, YAML, XML. I would personally go for this because I think you have the best support. XML almost looks good, but it's too verbose. And it's kind of falling out of favor compared to JSON. JSON is more compact and nicer, and there are a tremendous number of tools that can use it. If you do a web interface, I mean, JSON is then probably the most useful. You can do other formats, but then you don't have much support. Now, you're allowed and encouraged to use already good existing libraries. So what I'm not looking for is something built from scratch, piece by piece, with minute pieces. I would rather have you grab 10 libraries that are already mature and put together something that's really amazing and very useful, rather than you write a very, very sophisticated parser for what's in the messages. That's not particularly useful, right? So what I mean by that is, if you, for example, dump the messages in JSON, use a library to read the JSON in any other language. I mean, don't parse your own JSON. Don't do any of those things. It's perfectly fine to use intermediate libraries that allow you to do some transformations over the JSON, to do some computation over the JSON, or whatever. So this is maybe more an exercise in integrating interesting, I mean, good, useful things to produce something interesting rather than build things from scratch. Okay? Sky's the limit as long as you can define precisely what your contribution is. So I want to know what's your contribution, but a fantastic contribution is even finding the right 10 libraries that can actually help in doing some of those things. All right? Especially web-based technologies might produce extremely useful results. I mean, this is just a hint. It's not something I'm going to impose on you, but a web interface is by far the most accessible one, I would say, because just point your browser at the URL, and here you go. You can debug things, right? And actually, a lot of tools now start to have some sort of a web interface. Seems to be better. Okay. Any questions about this? So elegant solution for part one. The more elegant, the better. And then sky's the limit for part two. I want you to express yourself, to show off your skills. A lot of you bragged about the skills you have, and so I want to see those skills, right? in a way that actually allows you to take it further if you want, or show it off to employers, or just for the fun of it. For once, build something that's fun, right? Okay? Any questions? Okay. Now, if you want to pass some ideas, pass them, but almost anything goes as long as it's non-trivial work. I mean, that's what I'm looking for. I don't want to feel cheated that you found a way to do something in an hour or two. I mean, take it further than an hour or two. I mean, put a couple of weeks in it. All right? Okay. All right, so I do want to talk about failure. And I want to go through more kind of systematic material, mention some of the solutions and some of the core issues that exist in distributed systems. So things are going to get a little bit thicker in this part of the lecture. We already got broad views of what this fault tolerance is all about and so on. So let's just visit a number of core problems and core solutions. Now, we are moving in a territory where the interest is very high in some of these solutions, and to a large extent, the solutions I'm going to talk about did impose themselves in the industry quite a lot. So you need to know about these solutions, and it's not only a fuzzy idea of what you might do. Right? So one thing that I did not mention at all is this idea that redundancy is all over the place in engineering, and one approach to redundant systems is to use something similar to what they use in the rest of engineering, right? So we have computer science, but it's not really science. We have computer engineering, but it's not really engineering, right? I mean, now we are close to building a bridge, for example, where you go to prison if the bridge collapses, literally. Okay. In computer science, they always put a limited liability. If your power plant explodes, it's not my problem. You can get your money back, kind of thing, right? So to some extent, we have it the easy way, and we claim you can't have bug-free systems and all that stuff. So let's talk a little bit about this. I mean, one way to do redundancy is by essentially replicating everything. I mean, I don't know if you know, but for example, systems like airplanes have at least triple redundancy. So what does that mean? That means you have 3 independent systems that can control the same thing. Give me an example of at least a simple redundancy in your car. I'm sure all of you have driven a car at some point, right? Or wished you had driven a car. Well, it turns out that cars don't have particularly redundant systems, but they have a little bit of redundancy, right? So for example, you can drive the car both with power steering but without power steering as well. It's just much harder, but at least you can stop it. You have a handbrake and a normal brake, even though the handbrake can be used mostly to do tricks, to kind of fishtails and whatnot. But to some extent, you can stop the car kind of with the other brake if the primary brake goes down, right? Now, of course, airplanes have much, much more well thought out redundancy. Okay. And to some extent, you can think about this as over-engineering. Now, here is a general problem in software development that's not obvious at all. It's not obvious how to build redundancy in a software system. It turns out that with actors, it's much easier to build redundancy. Right? We already talked about one kind of redundancy. You can, for example, have a primary actor that's doing some computation, and if either it goes too slow or just to be sure, you ask another one to do the computation, and whoever finishes first goes. It turns out that that will produce a very nice, robust system. So that's one form of redundancy. And it's not so much a failure in the normal, traditional sense, but slow. You're slow, I can consider you to be failed in some sense and go on with this. So this is a situation in which you can use voting to provide redundancy, to mask failures, right? And it's something that does come from engineering, right? Now, the picture looks very crowded, and it turns out that the crowdedness is needed because, and I mentioned this to some of you, you see, the problem is not only that the primary system can fail, but whoever monitors the primary system or whatever else is going on can fail as well, right? So this did happen, for example, to NASA in one of the moon missions, right? They had a quadruple failure. 4 systems, all the systems failed that were watching the same thing, even though they were redundant and they were very different. Well, I mean, the conditions under which NASA has to deploy their tools is a little bit different than the normal stuff, right? But it's not clear at all if your things are really completely independent. I just want to mention that. I mean, even when you do actors. I mean, for example, if the power goes down in the entire city, poof goes your redundancy unless you can somehow deploy in multiple data centers that are spread all over the world or things like that, right? So there are some dependencies occasionally. I mean, in an airplane, right, if the airplane explodes, it doesn't matter what else is happening there. I'm just trying to point out that at some point, you can actually have multiple, even redundant systems going down, right? So in this situation, you use voting. And basically, if you have three elements that are all supposed, this is something coming from engineering. If you have three elements, they are all supposed to provide exactly the same computation. What you can actually do is say, I'm going to declare the correct result as the result produced by two of the subsystems. So that allows one of them to run amok completely. Okay? But it turns out that you need this complicated scheme to make sure that you protect against other components failing. For example, the voters failing. So you have a voter, for example, you can have voting circuitry, but the voting circuitry can fail itself, and this is why you, in fact, need to replicate everything three-way. Okay? I'm not going to go through all the details, but this is one way to provide some sort of fault tolerance. It's more relevant if you design circuitry, if you're getting close to hardware. Okay? So and we are going there because the thermodynamic noise starts to introduce bad signals everywhere, and some sort of voting or redundancy is needed. Okay? So that's one approach. It's not very popular in computer science unless you're designing some software for NASA, in which case you might do something like this. It is possible, though, with actors. Right? You would simply ask three actors to do the same job, and then you vote. That will, for example, protect against any faults, even in the computational logic. Right? And you can imagine, for example, Project 1 could have been done in that way. That way, for example, you're really sure that the answer is correct, right? At a minimum. Right. All right, now, when it comes to masking failures, the idea of groups, forming some kind of groups, it's crucial. And these groups will allow you to raise the resilience of the system to almost any level you want. But of course, then the group size has to grow and you have other problems. Right? So a core notion is this notion of K failure. So K fault tolerant systems are systems that can tolerate up to K failures, let's say. I mean, hey, this is just a definition. And then, of course, the question is how can you achieve this, where K is some kind of a constant, right? So a one failure, this is really what this system was designed for. So this is a one failure system. Right? We needed to have 3 copies of everything to provide resilience to one failure. Right? And you do that through voting. Now, this idea of voting is something that can be used to provide high level of failure, right? For example, a K failure system. So if K is 10, right, that means 10 subcomponents can fail and the system still runs okay. Now, how you pick that K and what matters in real life, and it really depends on the circumstances. I mean, it depends on what's at stake in the end. Right? Usually, the performance of the system degrades severely with K. I mean, if it degrades linearly with K, you're lucky. In some circumstances, it can degrade, for example, quadratically with K or things of the sort. Okay. Now, another trick that can be used, given the fact that the groups are very useful. So if you have a group, then you can do some kind of a voting in the group, right? So if you want K redundancy, probably you need the equivalent of the triple redundancy, maybe, I mean, intuitively, you might need, for example, 3K participants in the group, and then if K fail, the other 2K can outvote the K and work okay. If you're really lucky, you might get away with a 2K system, right? It's not quite clear what works there. So we have to consider various protocols to see how big the group has to be to have resilience for a particular K, I mean, to survive K failures. Right? Now, when it comes to groups, we can have flat groups, and that's mostly what we talked about before, right? Or hierarchical groups. Hierarchical anything scales better than flat anything. I mean, this is a rule of thumb in distributed systems. And this is basically how the humans organize themselves, right? This is why large companies have little groups. There are bigger or bigger groups, bigger or bigger groups, bigger groups, bigger groups, because otherwise it's madness. I mean, how are you going to even put together any kind of discussion with so many people, right? So you're going to talk more about these hierarchical groups, but the idea is always have some kind of a local coordinator and workers with some kind of a leader election algorithm. We talked about those previously, right? And then workers try to do the monitoring to detect if there is a failure and try to fire up some kind of a local leader election. But the coordinator, if it's still working, is going to be the primary, if you want, point of contact and relay messages higher up in the group and so on. And that will significantly cut down on a number of messages that have to be sent around. Okay. For flat groups, you cannot hope to grow them more than a couple of hundred nodes. I mean, literally the number of messages that have to be sent is overwhelmingly large. Okay. All right. Now, I want to make some refinements when it comes to distributed systems and how can you reach agreement. Let me actually give you an idea first what agreement is. But these are going to be the kind of cases we want to consider. And I need to discuss every single point separately, right? So let me give you a very colorful picture of what this agreement is all about. It's something introduced by Lampert in 1982, I believe. It's called the Byzantine agreement problem. And this problem is by far the most studied problem in distributed systems to start with, and has a very nice picture that comes with it, which you might have seen before. Okay. So here's how it goes. Okay. So you have the following kind of situation. This is a simplified situation. It's easy to generalize it to much crazier scenarios. So you have a hill, a valley, and another hill. Okay. I told you it's colorful. And we basically have two armies, but they have, if you want, multiple divisions spread all over the place. In particular, one of the armies is on the two hills. It has two parts on the two hills, right? So I don't know. I'm going to draw some sticky man here. Right, so this is the Roundhead army. So there's one general there with its army, another general here with his army. I can draw better than this, but I'm not going to take the time. Okay? And then we have another army, which is the opposing army in here. Let's make this guy a little bit better with a pointy hat. Okay? And the idea is the following. These two armies are too small on their own to successfully win any battle. Their only chance is to coordinate and to attack at exactly the same time the army in the valley. Okay? Now the trouble is, any kind of message exchanged between these two could, in principle, be intercepted by the guy in the valley. We're not sure if it gets intercepted or it doesn't get intercepted, but could be intercepted. The goal of the protocol that we need to come up with is to establish agreement between these two armies that at a certain given moment of time, for sure, they both attack. Now, of course, the danger is if they don't attack at exactly the same time, they get butchered by the guy in the middle and they lose the war. Okay? So they have to agree on a time. All they have to agree is at what time to attack. Nothing else. Okay, it's very simple, right? So then you can go through a number of scenarios, and we can walk through those things and see what could in fact help. And it's going to be surprising, but a lot of things that you might think help don't quite help. Okay? Now, what's built in here, and I want to make this clear from the beginning, is we don't want to achieve a high probability agreement. We want to achieve a sure agreement. Okay? Sure agreement is better than high probability agreement in general. It makes us feel more comfortable, as long as it's possible to achieve such agreement. Right? Now imagine what could actually happen. So let's go for a simple scenario. This guy just sends a message to the other general, say, let's attack at 7 a.m. tomorrow morning. Okay? Now, the message might or might not go through to the other guy. What we care about is what this guy thinks and what this guy thinks. We don't care about what this guy thinks. And to a large extent, it's irrelevant what this guy thinks. Okay? Unless this guy can reliably intercept all the messages, it doesn't matter what this guy thinks, because if both agree to attack at 7, this guy is toast. Okay? Good, so we're not worried about it. We are worried that this guy can intercept messages, unreliable versus reliable messages, right? But we're not worried about what view of the world this guy has. We're only worried about what the view these two guys have. So both of those guys not only have to know that they attack at 7, but they have to know that the other guy knows that they have to attack at 7, because otherwise you don't take the chances to attack. Okay. By the way, this has a name, and it can be formalized, and you can come up with very, very complicated logic-like math. It's called common knowledge. And it's a research area in itself, and it's complicated. Okay, I took an advanced class at Cornell about this. I'm not going to go into details, though. Okay, good. So this guy sends the message. Now, again, this guy might or might not get the message. Okay? So scenario number 1, this guy doesn't get the message in the first place. Well, this guy, knowing that the message gets lost, right, he doesn't know if the other guy got the message or didn't get the message, and could have not got the message. And this guy, let's say, he didn't get the message, so they don't do anything. Well, by the way, doing nothing, it's easy. But the assumption is we have to do something, because otherwise there is a penalty. Let's say within 3 days, something bad happens if we don't agree, because otherwise you can just do nothing and say, we don't need agreement. Right? So one way to solve all the problems is to say, I have no problem. but that's not an option here. Right? So scenario number 1, the message gets lost straight out. Scenario number 2 is the message doesn't get lost, and it makes it all the way through. Okay? This guy got the message, but now the trouble is, okay, so this guy got the message, but how does he know that the other guy knows that he got the message? Again, they have to both agree that something is true. Right? So what could this guy do? He could send an acknowledgement, right? OK, fine. Let's say the acknowledgement does get or doesn't get here. Now, if they both agree that the protocol is I send you a message and you send an acknowledgement, if this guy doesn't get the acknowledgement, he's going to freak out and say, possibly my message didn't get there in the first place. He has no way to tell if the first message didn't go through or the ACK didn't go through. So he still won't attack, because I don't know if I can attack or not. But what about the knowledge of this guy? Well, he got the message. He knows that the other guy sent the message. He sends the ACK, but has no way to know if the ACK comes back. Say, OK, but let's send an ACK to the ACK. And right, keep on piling them up. Well, it turns out that we're going to go through these scenarios. Unless certain strong assumptions are true, they can never possibly agree for sure that with a finite number of messages, that they both understand in what state they are, whether they attack or they don't attack at 7 a.m. Okay? And things are actually harsh, and you're going to see in what sense they are harsh. So to a large extent, this is the worst scenario possible, right? Because the messages can get lost, and we assume that it takes a while for the message to go through, and it's not quite clear how much time it takes to go through. Right? So things that are going to matter is whether the messages are synchronous or asynchronous. Right? Synchronous means the messages are sent on some kind of a clock. Now, if they are sent on some kind of a clock, right, then essentially you know for sure how much time would have required for the message to go through, right, because they are sent on that clock. A relaxation on the clock thing with a synchronous or asynchronous system, right? So synchronous really means you cannot communicate at any time. You only have to communicate at certain, if you want, bits. A relaxation of that is communication delay is bounded or not. Okay? So you see, a problem you're going to have in this system or in any other system is, can you make some assumptions about if a message is delivered within, let's say, 3 minutes, or 10 minutes, or 5 hours, or 10 milliseconds? Okay? So if you have a bound on the messages, you're in a better position. Why? Because you say, look, my message should be delivered within, let's say, 1 hour. This guy, when he gets it, probably will act on it very fast and send an ACK within 1 hour. If I don't get something in 2 hours, something wrong happened. You're in a better position. It's not clear that solves the problem, but you're in a better position. Right? The same thing happens in distributed systems. Right? If you know for sure that the message should have gotten on the other place within, let's say, 100 milliseconds, not getting the message, right, could allow you to say, at least with more certainty, that the message got lost. Okay? But you see, in general, so we already know that synchronicity is virtually impossible to achieve on a very fine scale. Why? Because it requires perfectly synchronized clocks. We have to agree that we send messages at a very specific time. That means perfectly synchronized clocks. Communication delay is bounded or not? Well, it turns out that none of the technologies we use guarantee that if a message is delivered within a certain amount. You're allowed to lose it, but if it's delivered within a certain amount. Now, you could enforce that, for example, by artificially dropping messages if somehow they have a timestamp and you have something that resembles some sort of a clock. Right? That can be done if you have a very coarse understanding of the clock, but in fact, you need more precise numbers. Another thing that could help is message delivery, it's in order or not in order. So if messages can get scrambled, that creates its own problems. Okay? And another parameter in the whole story is going to be whether you do unicast or multicast. Unicast is point-to-point communication. Multicast means you send it to all of them, but you send it for all of them as some sort of an atomic operation. We're going to talk about that later in the context of atomic multicast. Okay? Good. So instead of going through proofs and things, I'm going to just give you a table. And the table tells us what's possible and what's not possible. And for every little thing in the table, there is a proof in distributed systems saying, yeah, the X is justified. Okay. Textbook, by the way, has it exactly the other way around. Okay. They managed to put X's where you have the yeses instead of the check mark. X means not possible. Right. So in particular, if you have, look at this. If you have unordered messages, I'm sorry. So the unordered messages don't do so much. Oops, what did these guys do here? Right, so let's analyze some of them, right? So usually, synchronicity is better than asynchronous. So in more circumstances, you're going to be fine, right? So if you're synchronous, as long as, so this is, okay, ordered by unicast. So okay, so let's read the table a little bit. So this square corresponds to synchronous, unordered unicast. This one, which seems to be the worst, right? It's asynchronous, multicast, and ordered messages. Does it even matter? One second. I think one of these tables is messed up, either the one in the textbook or this one. Yeah, that's great. Okay, so the bottom line is the following. I don't expect you to look at this table. Is synchronicity usually helps. Okay, if you have synchronous messages, life becomes easier, and you can achieve agreement easier. Other things that actually help is whether you have multicast or you only have unicast. So a little bit of multicast helps, especially in the combination with asynchronous. If you have, this makes absolutely no sense. Wait a second. Yeah, so whatever this is, it's basically completely weird. Okay, I think the one in the textbook, but with the reverse arrows, is the correct one. Right, so the kind of, so synchronous always helps. Synchronous is good across the board. The moment you have synchronicity, you can actually prove this. The moment you have synchronicity, you're good across the board. Why? Because essentially, if you can send messages on a heartbeat, right, then it's very easy to say if the message got lost or didn't get lost on the other end. If you did not get message in this timestamp, the message got lost, and that's the end of it, right? Or if you got a corrupt message. Then the kind of things that help a lot, it's also multicast. If you do have reliable multicast, you're good no matter what, because that's essentially what you need with this, with the generals. Multicast means I can reliably either deliver the message to both or not deliver it to any of them. So if you have any multicast mechanism, it doesn't matter how you achieve that. If you have any multicast mechanism, so-called atomic multicast, deliver to all or don't deliver to anybody, you're fine. That's basically what the problem is. I mean, one way to, I mean, the multicast implementation, it's a direct implementation of the agreement protocol itself. Okay? Now, if you have neither synchronous nor multicast, the other one that is going to work is if you have synchronous, I'm sorry, it's only the combination synchronous and I'm sorry, synchronous and bounded that works. Right? But that kind of suggests that it goes together. You can have synchronous plus unbounded, and this is going to work fine as long as the messages are ordered. So these are the only combinations that work, okay? Synchronous bounded, it's fine. Multicast of any kind, it's bind. And synchronous plus unordered, I'm sorry, plus unbounded but ordered, that seems to be fine as well. Okay. Now, details don't matter that much. The important thing to remember is a lot of the combinations don't work, especially asynchronous. So again, ignore the table here. Asynchronous messages, which is really the norm in any kind of communication, have the problem that I just described, right? You send a message, you send an ACK, but how do you know you got the ACK, and you send the ACK of the ACK, so on and so forth. Okay. Now, in practice, we have good enough solutions that don't need to achieve that for sure. And if you really look at all the details of how things actually work in practice with the mechanisms we can actually build, you can in fact prove that unless you assume that certain components are in fact make the transition from very probable to correct, you're never going to actually achieve any kind of agreement in fault-tolerant systems. Right? So from a technical point of view, it's impossible to actually achieve agreement in fault-tolerant systems unless you just assume that some of your components made the transition from highly probable to correct. Okay? All right. Now, let's see a little bit of a protocol that will allow us to deal with faulty systems. Right? So this is the kind of stuff that could work with those rogue generals, the pointy head generals that are in the middle. Okay? So here's what we have. This is a so-called Byzantine agreement protocol, and that was proposed by Lampert. Okay? The idea is we want to get an idea of what the state is for all the non-faulty processes. So essentially, every process has a number. And what we want to get is to recover the state. What is the number that every non-faulty process has? Now, we cannot possibly recover the state of a faulty process because we are going to assume that the faulty process can lie about anything. Can lie during the protocol, can lie about what its own value is, or might not even have a value, for all we know, right? So you have to be careful what the standard is. So you cannot say, I know the state of all the systems. You can only say, I know the state of the non-faulty systems, right? Good. So one such protocol proposed by Lampert is similar to the vector protocol that we had for the vector clocks. In particular, the message exchanges are going to contain all the known values for, my view of the state, how I think the state is for everybody that participates in the entire protocol, and some sort of a voting is going to go in there to determine whether a value is reliable or not reliable. Okay. So in the message exchange, right? Okay, so let's see. For example, one is going to maintain its own state about what it thinks the state of all the other ones are. And remember, right, so we are going to use the letters X, Y, Z, and other letters A, B, C, D, and whatnot for the values that could be arbitrary because of the faulty guy. So what happens with the faulty guy is when the faulty guy reports its own state to anybody else, right? The faulty guy was guy number 3, right? So in position 3, the faulty guy is going to lie, so he's going to put whatever value it wants in there when it reports directly the value to any of the other machines. When they are exchanging these vectors, it can exchange completely arbitrary vectors. We have to assume that it could go anywhere from correct to a complete lie, right? So this is the way they recover the state from the direct messages, and these are the vector exchanges that go in between, during the protocol, during the communication. So the participant number 1, the actor number 1, is going to get the value 1, 2, Y, and 4. This is going to be from guy number 2. It's going to get A, B, C, D for guy number 3 because it's completely faulty, and 1, 2, Z, 4 from guy number 4. Again, the Y and the Z are here because we assume that they are completely arbitrary values that the faulty system produced. Now, one thing to keep in mind is these kind of protocols assume a certain kind of consistency in the system, a certain number of assumptions that are true. So in particular, when one is reporting its own value to all the other guys, it reports the same value. But the faulty system is not necessarily going to do the same thing. So it might report one value to 1, completely different value to 2, completely different value to 4. Right? This is why we have this Z, Y, and X in here. They might or might not be the same thing. Okay? Good. Now, similarly, 2 got a certain set of vectors and 4 got a certain set of vectors. Notice that whatever information comes from 3 is completely garbled, potentially. Okay? Now, nevertheless, from these vectors, they can actually use a voting system and simply say the majority vote on each of the components to determine what the reliable, and you can Lampert prove that this is correct, what is the reliable state value for particular other participant. And again, they have to guess, I'm sorry, not to guess. They have to determine the state of all the non-faulty systems. So let's look from the point of view of participant number 1. According to the voting, it's going to say 1A1, so 1 wins, 2B2, 2 wins, Y, C, Z, God knows what's in there, whatever, 4D4. So it's going to correctly guess 1, 2, whatever, 4 as the state of the system. Okay? It turns out that's exactly what 2 is going to do and 4 is going to do, right? Again, if you do majority vote, you're going to get 1, 2, whatever, 4, 1, 2, whatever, 4. So according to this protocol, as long as we have only one failure in the system, everybody's going to recover exactly the same view of the entire system except for the guy number 3 that's actually faulty. And to some extent, they even detect that it's faulty. Well, so depending on precisely what game Z plays, they might or might not get contradictory values for number 3, but that's fine. Okay? Now, it turns out that the number of participants and the number of failures that can be accommodated are tightly related, right? So this is, for example, a situation in which you're not going to get a good answer, in which you have 3 participants and one of them is faulty, right? If you run through the protocol, right, you see 1 got 1, 2, Y, A, B, C, 2 got 1, 2, X, D, E, F. There is no voting you can possibly do to derive the correct value. And Lampert essentially proved that in order for this system to work, to accommodate K failures, you need 3 K plus 1 participants, right? So K faulty need 2K plus 1 healthy for a total of 3K plus 1, right? So basically, if you use this rather heavyweight message exchange, in which everybody first exchange, they exchange the value and then they exchange the vectors with respect to what their view of the system is, in order to allow 10 faulty systems, you need 30 plus 1, 31 overall components in the system. Yes? Well, you have to do majority, but remember, it's not enough to just do majority. So you see, here you have 2 participants and 1 faulty. So you might think that this guy can outvote the other one, but it's actually not true. If you run the protocol, right, you simply don't get enough information from the other ones to complete the voting, right? So it worked here. So you need that plus 1 that's missing in the other one, right? So in here it worked because you did get 2 healthy messages with a damaged component, almost healthy messages and a completely bogus message. Then the 2 almost healthy one can outvote the bogus one, but that doesn't work in this circumstance, right? So I'm not going to go through the details, but you can actually prove that if you don't have precisely 2K plus 1 healthy one, this protocol will not allow you to outvote the K faulty ones. Right? All right, good. Now, another topic. I mean, when it comes to faults, we can say we want fault tolerance everywhere, right? So we can start with simple scenarios and make our way up to more complex scenarios. One of the simplest scenarios is remote procedure calls, right, if you have failures. Now, a crucial question is what kind of failures you can have in remote procedure calls. These are the simplest things, just that basic client-server architecture, right? The client asks the server to do something, the server comes back and gives the answer. So what could possibly go wrong? Well, almost everything, right? The client is unable to locate the server. What do you do then, right? So what can you possibly do when the client is unable to locate the server? Well, so here is one thing to keep in mind. What you would like is solutions that are as transparent as possible. So you want to bother the actual end user as little as possible. But I mean, for example, if you cannot locate the server, I mean, many things can actually be wrong. Some of them could be you literally have no internet connectivity, right? I mean, then you have to expose it somehow. Unless you have a mechanism to somehow try to remedy the situation, there is very little you can actually do. So at some point, you have to give up and say, yeah, the user has to be notified that potentially I can't. I mean, this is a situation where you even ask the operating system, is the networking up, for example, right? What other things can actually happen? Well, all the servers are down, depending on the redundancy or non-redundancy of the system, right? Right. So usually there is, this is a very vulnerable point in which there isn't much you can do beyond simple stuff, and you have to propagate the error all the way to the end user. Okay. Request message from the client to the server is lost. So what do we do in those kind of circumstances? So the client has, I mean, it found server. I mean, by the way, finding the server really means what? I mean, you resolve the DNS name, maybe, or you establish the initial TCP IP connection or some other connection, right? Now, the message request getting lost is relatively easy to deal with if you use this connection-based communication like TCP, right? TCP literally will report the connection is broken if there is any message that doesn't make it through in a certain amount of time, because it provides fault tolerance already. So this is already a situation in which we have a basic mechanism that's in fact reliable and doesn't bother the higher up application too often, and has been perfected over 30 plus years, TCP, right? It helps tremendously to build high level protocols. Okay, so don't be shy about it. Don't go to UDP unless you really want to do something like video, and you can literally tolerate and skip information, right? Don't try to build your own redundancy in the system. Okay, so TCP would completely solve this, but if not, I mean, some sort of a mechanism with potentially some kind of a timeout could in fact be used to declare the message as being potentially lost, and then what can you do? You reissue it. Right? For example, your browser does this all the time, right? You try to go on a website, and it's going to try to go there. It might expose it all the way to you and say, hey, the connection failed, but it already tried several times by that time, right? Or even try more. They had something like this, for example, with the phone systems. They probably still have it, but I mean, smartphones already incorporate things of this sort. For example, if you want to reach somebody over the phone and the phone is busy, they have this auto dial systems in which they keep on trying until the call goes through. Right? That's, in fact, some form of redundancy of exactly this sort, in which the request message cannot make it all the way. Or maybe to some extent, it's exactly like locating the server. Okay. Now, it gets more interesting beyond this point, because up to this point, nothing really happened on the server, right, potentially. But there are some issues we have to revisit. The other one is the server crashes after receiving the request. Now, you see, when it comes to this request, it's very important to understand what properties the request has, and if certain things can be tolerated. Okay? So let's draw some pictures to clean up the situation here. So it really matters what is it that the effect of the message is going to be. Okay? So when it comes to this kind of, if you want, the consequence of sending a message, we can think about messages that can tolerate various kind of semantics, right? One of them can be at least once. The other one is at most once. And ideal one is going to be exactly once. This has to do with when can you reissue the message in case you detect somehow that the message got lost. Okay, so the first one, at least one, says you can issue the message, but at most one time. Why? Well, you might have application-related reasons to say if you issue it multiple times, you could do more damage than good. I'm sorry, at least once means it has to go through, so you send it once or multiple times, and it's OK to send it multiple times. At most once is you send it at most. If you send it, even if it got lost, don't issue it again because something bad is going to happen. Now, either of these are potentially problematic. I mean, you could, in certain applications, argue that you can kind of tolerate them, but they are not ideal. By far, the most ideal one is exactly once, and this is, for example, what you would use in financial transactions. When I say, hey, move $10 from this bank account to this bank account. In the situation when, for example, server crashes or doesn't crash or whatever, I still want to make sure that the transaction went through exactly once. The reply message, we have to come back to these issues. The reply message from the server to the client gets lost. Okay? Now, it almost feels like there is no difference from the client's point of view where the message to the server got lost or the message from the server got lost. Right? But in order to enforce any of these semantics, it does matter. And obviously, the server has to participate in some sort of a potentially complicated protocol to ensure that we can enforce especially this one. And then the last one is the client crashes after sending the request. Right? Now, there is a particular problem in here that we have to be aware. And we need more pictures to support this, which I do think I have on the slides, which is even on the client side or on the server side, you have multiple stack components participating in the whole activity. And this kind of semantic, at least once, at most once, and exactly once, or other kind of transactional semantics, have to be imposed from the point of view of the end application, not from the point of view of the network stack. Right? So what we have to be worried about is not only the fact that something could have happened with the message while transported, but something could have happened with the message while delivering it to the application. For example, it doesn't matter that the network stack got the message correctly and even send acknowledgments to the server that say, yeah, good, not on my hands anymore. But if, for example, the client application crashes in the process of getting the message, or in between, the message got received by the network subsystem and is delivered to the application, it's still a crash. You still have to deal with it, right? Now, you might have different ways to deal with it, but from a user's point of view, it still didn't go through, okay? It's still a failure, and it has to be dealt with in this way. So in order to allow this kind of a distinction, right, some papers in the distributed systems literature, right, make the distinction between message delivery and receiving the message. So we say a message is received if it got delivered at the network subcomponent, but the message is delivered when it's actually passed to the high-level application. And things can still crash. Remember, crashes can happen everywhere for whatever reasons. Okay. Now let me ask you a question about, for example, push-sum, the protocol you implemented in, what was that, Project 2, right? So push-sum had a weird property. That's not quite obvious that it does this. Right? To a large extent, it sends the value multiple times, so it has some sort of at least one semantic. It tries to send it multiple times, and it seemed to work irrespective of how many times you send the message around, right, somehow. So imagine other kinds of computation that you might actually do in which you could send the message multiple times. For example, imagine you need to compute the minimum value across a value that's hosted at each participant in a distributed network, right? So the protocol can go like this. When I receive a message, I have an idea about what the minimum is. When I receive a message from it doesn't matter where, I compare the minimum on the message with the minimum I know of and take the minimum of the two. Right? Now, could I tolerate replicated messages? Now, this turns out to be very important because if you can be aggressive and send more than you need and get the job done with high probability, right? So when you compute the minimum, can you tolerate multiple messages, duplicated messages? The answer is yes, right? Why? Because the operation itself, it's a so-called idempotent operation, which means if you apply the operation multiple times, you still get the correct result. But when you compute a simple summation, it's definitely not idempotent, because if you add the same value multiple times, you're going to change the overall sum. And that's true also for the average. Okay? So somehow push-sum managed to transform a non-idempotent operation into an idempotent operation by this funny thing in which you were sending those weights and somehow things converged. I mean, it was done in an approximate sense, but it still worked, right? So now, this is something that in general would be highly desirable if you could accommodate, if you could transform non-idempotent operations into idempotent operations by any mechanism necessary. I mean, sometimes you can do it by essentially just trying to remember history and discarding things that are not useful anymore. For example, even when it comes to the sum, and some of these mechanisms could be used in this case, right? Even, for example, in the case of the sum, if you can afford to, in fact, keep track of every individual value that goes into the sum, and you have IDs in the messages that are exchanged, right? Then basically what you do is you maintain some sort of a vector or a dictionary or whatever else you want that goes from an ID to value. As you receive values, you're going to say, hey, did I receive this value before? If yes, discard it. You transform it effectively in an idempotent operation. If not, put it in my array. Now, obviously, you need memory proportional with that, and then computation proportional with the number of total values in the system. You do achieve some sort of agreement with high probability depending on gossip-like protocol or whatever else you have in there, right? But the price you pay is large amount of memory and large amount of the computation locally. Push-sum had very little computation locally. You just, right, in the end, you needed only a logarithmic number of operations to patch whatever partial values you had. But those are very funny kind of algorithms, right? Now, you don't see that many of them because it's usually hard to prove that they do anything that's useful, right? But that's a highly desirable thing if you transform a non-idempotent into an idempotent. Okay? All right. So let's go for some of these issues and let's see how certain things like this can be resolved. I mean, these are some scenarios we can go through, right? It's exactly what we had before, right? You send a request, you send a reply. This is not much more different than the agreement for the Byzantine generals situation. Right? I mean, to some extent, you have to agree that the server did a certain operation, and you know that it did a certain operation, and then for sure you know that you move from one state to another if you want in the client side. Okay. Right? So you can, so in general, when you propose a protocol, you have to explain how various scenarios in which the exchange can actually happen can be dealt with. And the protocol must have provisions for that. The goal being that both the server and the client agree on what actually happened. As long as that happens, right, you can in fact correct the situation. So for example, one of the assumptions usually made is that the same request can be issued multiple times. And that's relatively easy because you simply cache the request on, let's say, the client side or things like this, right? So if the client detects correctly that something bad happened and knows for sure that the server knows also that something bad happened and discards any kind of results that it would have had, a simple reissue would work. So what happens is, in the end, you want to start having some transactional semantics in there. To do things of the form, begin transaction, do then a sequence of operations, and then have a commit on an abort, and have all the parties agree whether it's a commit on an abort. That would definitely solve this issue completely. Because it's either the case that the client's transaction commits, which means the message commit got delivered to the client and everything is fine, and then the server knows it commits. Or there is an abort, and then both the client and the server know that the whole thing got abandoned, and it's server's duty to make sure there is no influence of that particular operation at all on the state of the server. Okay? So I'm not going to go through all these scenarios because they are kind of boring, right? But these are potential things you could do in a system like this. Okay? So you can have multiple reissue strategies from the client's point of view, namely do again the operation, and they are appropriate or not so appropriate in various circumstances. Let's see a little bit from the client's point of view what could happen and from the server. Now keep in mind that in fact none of these guys are guaranteed to be perfectly correct, right? Unless you in fact implement a heavyweight mechanism like transactions. Okay? So for example, for the client strategy, right, we can essentially always reissue. I mean, if you always reissue, it has to be the case that the server keeps track of enough information to make the operation idempotent. For example, a safe way to do that would be the following. Every single request will have some kind of a unique ID. The server has enough memory to keep track of all the unique IDs. If that's the case, so if the client has any doubts that his request went through, it sends it again. If the server has enough memory to keep track of all the requests, and the requests have a unique ID, the only thing the server needs to do to make the operation idempotent is to check whether, did I do this before? Yes, good. Move on. So you have a minor problem there, which is make sure that you have unique IDs for all the requests, but this definitely will significantly help in making sure that both the client knows that things went through and the server keeps a consistent state of the system. Right? So you can walk through scenarios. It doesn't matter if the message got lost from the client to the server, or the message back, or the delivery of the message in the client system went amok. If you can reissue the message, for example, through this mechanism that I just said, namely check whether you satisfy the request before, otherwise throw it away, then until the client is satisfied, namely got the acknowledgement, you're fine. Right? The server, for example, will know that the client will come back and reissue the thing if it didn't get the correct acknowledgement, and the server just has to respond with the correct acknowledgement if that actually happened. This is essentially what can happen, right? So when the server gets the message, if you already satisfy this request, all you need to do is send the acknowledgement. If this is issue and wait for acknowledgement kind of protocol. Okay? Now, in general, depending on how many participants you have and so on, you have to be careful with these acknowledgements, and that's something I want to talk about in another scenario. Because especially when the message has to go to a lot of participants, you're going to have a big wave of acknowledgements that have to come back that can actually overwhelm the server. Okay? I'm not going to go through all of these things. Okay. So when you have such multiple participants, the name of the specific activity you want to do is reliable multicasting, right? Now, the way to think about how distributed systems are useful, notion is that distributed systems and libraries and building blocks in distributed systems are useful, is you want to have implementation of a set of primitives and then to build your entire application on top of those primitives. As long as those primitives are implemented in a nice, sturdy, reliable way, the application design becomes much simpler and much easier. To a large extent, that's how we use TCP, right? We know that it does all the magic, congestion control and acknowledgements and whatnot, and all we have to worry about is, okay, follow the protocol to open a connection and then put things on the pipe. And essentially, the network stack through the operating system is going to tell us when something ran amok, and then we know the connection was down, and that's the end of it, okay? And in fact, we will know for sure that our message, whether our message got delivered safely on the other side or got delivered safely on the other side, right? That massively simplifies the application design. The same thing goes with the reliable multicast. If you have a reliable multicast component, the application design becomes much simpler, right? For example, a chatting application will need something like a reliable multicast if it's really important that all the participants see all the activity in the chat, right? So with such a facility with reliable multicast, when somebody produces a new message, the reliable multicast mechanism will distribute it to all of them. But of course, the question is, what exactly is this reliable multicast, and what specific requirements we are going to have on reliable multicast? Now, one of the most convenient types of reliable multicast, right, is going to be something called atomic multicast. Okay, you can go worse than atomic multicast in terms of complexity when you have totally ordered atomic multicast. So atomic multicast refers to the fact that it's either the case that a multicast message is delivered to all the participants or is delivered to none of the participants. Now, this is from the point of view of the application, not from the point of view of the network stack, right? So this is very important to understand and to make the distinction. It's not so much that somehow magically we don't deliver things to the network stack, but the network stack, if it follows the protocol that implements the atomic multicast, will not deliver the message to the application until it's sure that all the other network stacks got the message, okay? Now, an atomic multicast makes the life of the developer very convenient because you never have these false messages going around, right? So, I mean, performance could suffer, but that's always a potential problem, and it's a different issue. But in fact, if you printed something on the screen, for example, in a chat room, if you printed something on a screen of one of the participants, you essentially guarantee that it gets printed on all the participant screens if you have atomic multicast. Okay. Now, when it comes to how do you implement multicast, a big issue, I mean, we already know that acknowledgements help, right? And acknowledgements are, in fact, crucial to at least achieve a very high reliability of delivering the messages. But the question is when to acknowledge. And when do you send acknowledgements? And what alternatives do you have to acknowledgements? Okay? So, for example, things can work in this way. You have the sender is going to send the multicast, and essentially the multicast will result in all the receivers receiving the message. But of course, the sender doesn't know which receivers got the message and which receivers didn't get the message, right? So the question is, what information do you need to send back to the receiver to make sure that, for example, you have a full implementation of something like atomic multicast? Now, an obvious solution would be send acknowledgements. But look, if you have a multicast that has many, many participants, you get one acknowledgement for each of the participants. Now, keep in mind that you can have schemes in which the multicast does not involve point-to-point connections to send all the messages, in which case you would just double the number of messages. Right? So, for example, if the implementation consists in a separate TCP/IP connection between the sender and all of the receivers, you're going to have anyway the acknowledgements going back on the TCP/IP connection. But if you have cleverer schemes, and for example, such schemes are used by BitTorrent, right? If you have clever schemes and you form a hierarchy, it's similar, for example, to the phone trees that used to be very popular before they had this automatic phone call mechanisms, right? Then, in fact, because every participant does its own job at propagating the message, having acknowledgements is going to be devastating, right? So to give you an idea, the sender might actually send a message to few participants who propagate it further in multicast. And this is the kind of multicast, for example, that's used by the routers. It's not activated because it overwhelms the routers, but, right? Then, in fact, the number of message exchanges by any of the participants is relatively small, but an acknowledgement, right? You're going to get an acknowledgement for each of the nodes in the tree, and that's going to be overwhelming, right? So this is why it's very important to investigate ways to avoid such large number of acknowledgements. And this is where an interesting notion comes into play, which, I mean, it's under your nose, but you don't think in that way. People don't think upside down, right? Which is negative acknowledgements, right? So a negative acknowledgement is essentially exactly that. It's the opposite of an acknowledgement. If you know you should have gotten a message, and you didn't, you send a negative acknowledgement saying, I somehow didn't get this message, right? It turns out that TCP/IP will use a combination of acknowledgements and negative acknowledgements in the fabric of TCP/IP. And in particular, when one frame is missing, right? So you have some sort of a sequence in which, a sequence number that has to tag every message. If after delays or whatever in the protocol, if you're still missing some of the messages with a particular sequence number, then you send a negative acknowledgement saying, I'm missing this guy, you have to send it to me. Something similar could be used when you actually do multicast, especially in protocols in which you send a succession of these messages, right? So if you got certain messages that are further away and you're missing some, you can send negative acknowledgements to say, I'm missing this thing. And this actually plays very well into networks that are mostly reliable, which is in fact the case nowadays. So a lot of the fault tolerance discussion and the fault tolerance technique and the whole hullabaloo about fault tolerance, it's about that now reasonably remote possibility that something goes wrong. Usually if you have a system in which most of the time things go wrong, then things are bad. And you can in fact prove that you can't make much progress in the system. But if you have a system that's very reliable, but you want to raise it up to fully reliable, namely to put lots of nines in the reliability factor, right? Then negative acknowledgements are far more useful. So you can, this is a more, if you want, optimistic view of the world. So instead of being paranoid and trying to check everything, what you do is you have a mechanism to detect that's slower, to detect when something went wrong, and only act when something went wrong, right? Hence, this negative acknowledgement. So if, for example, it's very probable that the vast majority of the participants in a multicast will in fact get the message, and only very few won't, with negative acknowledgements, you cut significantly down on the number of messages that actually have to go back, right? But again, you have to justify this optimistic assumption by reliability of the system in the first place. But in fact, things are very reliable, right? So even when it comes to computation, we are going to come back to computation a little bit later in the class, right? MapReduce and whatnot. The vast majority of the participants are going to be up and running well. It's just the occasional one or two that are going to hiccup, right? These optimistic algorithms are now, in fact, favored almost everywhere, right? Because they tend to work much, much, much better under highly reliable systems, right? So rather than have this massive message exchange, again, you're just going to exchange messages when you detected that something went wrong. But it's important to understand that you need to find a way to detect that something went wrong, right? Possibly, you know there is a sequence of such messages, you have a sequence number, and you're missing a number you're missing a message in the sequence. Or you know that you should have gotten a message within a certain amount of time and you didn't, or something of the sort. Okay. When that's not possible, you need acknowledgements. Okay. Now, I mentioned the fact that hierarchies are good in general, and they are one of the ways to make anything in distributed systems scalable. I mean, let me just mention a type of hierarchy that's anyway imposed on you. Okay. So one of them is the fact that, for example, big cloud companies now have multiple data centers. That already forms a hierarchy, which is kind of a geographical hierarchy, right? But it gets a lot better than this. And because of the way networks are put together, you in fact have some sort of a hierarchy. The closer you are to the native hierarchy, the better you are with a hierarchical algorithm. So let me just explain, right? So usually, when you have a distributed system and you think about participants, you have to be worried about the latency. And of course, a crucial question is, what's the latency? Now, if you have a very large system that spans multiple data centers, you have to assume the latency is the worst, namely the largest latency in between two data centers. But in fact, that's not necessarily the case, depending on how you organize the computation. Okay. So whenever you talk about distributed systems, you have to understand that they are running on something. As long as you don't have too much virtualization going on, and you could, in fact, decide how to form the logical hierarchies with respect to something in the hardware, you could do much better than just randomly putting the hierarchy. Okay? So the picture I want you to have in mind is the following. You have, well, let's draw some stuff in here. So you have one computer that itself is going to have multiple cores, and you might use virtualization or you might use multi-threading or whatnot. to allow, in fact, a mini distributed system to go on in there. And it's better to think about them as distributed systems and use distributed system techniques. Okay? If that's actually the case, I don't know, you have some hard drives and things in here. If that's actually the case, then the latency of communication in between participants within this machine is going to be very small. Right? Now, we are not talking quite nanoseconds, but microseconds for sure. Okay? So it's not a problem within few microseconds to have two processes talking to each other. So within one machine, you're talking about microsecond latencies. Right? Now, if, in fact, you place your machines in a rack, I'm sure you've seen at least pictures of these racks. Right? So now you can have these high-density servers, or 1U, which is 1.1 inch and 3/4, or 2Us, right? And they have enough screws to mount them on a nice metal thing. I think they have some of these metal racks hanging around on the 3rd floor somewhere in a corner. You can see them, right? So these servers, you can pack them quite densely. They now have actually super high density such things, right? And presumably, you're going to connect them through some sort of a network, right? Then you're going to have basically a switch here, which could, in fact, be a high bandwidth switch. I mean, an expensive switch or not so expensive switch. Even the not so expensive switches now have very small latencies. You're talking about a fraction of a microsecond, right? So the latency is usually 1/10 of a microsecond. It's still 100 times worse than, I'm sorry, a millisecond. It's about, if you want, 100 microseconds. It's 100 times worse than this, which definitely is 5 orders of magnitude worse than the nanoseconds you can get when you go to the cache and whatnot, right? But it's still pretty decent, right? So as long as you stay within a rack and you have a decent switch, you can still have relatively small latencies. Now, when you move in between racks, the latency goes up, and usually by another factor of 10, right? It reaches the millisecond. When you start moving now in between large geographical areas, it can climb up to hundreds of milliseconds or higher. So what's actually happening is the physical systems themselves, in fact, form a hierarchy, because that's the way we put them together with components, right? So this switch can accommodate, let's say, 24 ports. That will allow me to connect up to 24 machines. Well, I can put 24 machines in a rack or 22 or whatever to leave room for the switch, right? So because each of these components themselves that glue things together have limited capacity, right? And then you glue bigger components, right? A normal hierarchy forms anyway, and this is really how the internet is built, with more redundancy and more things, but it's still some sort of a hierarchy. If you, in fact, map hierarchical organization for your specific protocol right on top of the hierarchy formed by the architecture, you, in fact, can get extremely good performance. So what I mean by that is, if your protocol, for the most part, with the most participants, tries to stay locally and go globally rarely, then it doesn't even matter how many messages you actually exchange, as long as it's not an exorbitant number, if most of the messages are in fact local messages. So you can send orders of magnitude more local messages for the price in latency that it will take to send a global message, right? So even if you need to do massive coordination, it better be the case that the way the coordination works, if you use a hierarchical method, which you should, tries to go directly on the specific architecture you have. And for example, for the problem you dealt with in project number 3, which is the distributed hash table protocols, a big problem with them, and they try to remedy this, is the fact that you mask any kind of locality you might actually have. For example, this kind of locality, right? That in fact means that the cost in latency of any message is the average cost to cross the large network. So if you have a large, widely spread such deployment of a peer-to-peer system, then you might not have that many message exchanges. It's a logarithmic number to reach any participant, but you pay full price for all of them. If you find a way to have a lot of those connections to, in fact, be local, you could speed up significantly the actual real time it takes to run the protocol to achieve any of the things, right? And that's when they started to design some sort of a hash functions that are not quite hash functions, and they can take into consideration this kind of locality. This is what locality means, right? So when it comes to improving the performance of a distributed system, again, one way to do it is to use some sort of a hierarchical scheme if you manage to match that hierarchical scheme with the natural hierarchy formed by the actual networking, right, your performance is going to be significantly better. Okay? So, for example, even if you need to carry out a very large computation, if you have a local boss for each of these tightly packed networks, right? So usually the rule of thumb is you want to have a coordinator per machine if you have multiple cores. You want to have a coordinator per rack, a coordinator per building, then another one per, I don't know, data center, and then you're probably done. Okay? So all of those ideas have been explored in these hierarchical systems. Now, also when it comes to these failures and retransmissions, you can actually blend them into the hierarchical protocol. In particular, how can you implement a multicast algorithm? Well, you can start from, so it doesn't matter where you start, right? For example, the message maybe starts from one of the elements in the rack. It's sent then to the boss for the entire rack, who sends it to its boss, the entire building, who sends it higher up, higher up, higher up. And then once it reaches the top, it's going to be disseminated again boss by boss, but it's going to go in parallel and distributed to the entire system. Okay? This way, you're really trading off, if you want, well, I mean, if you would have a reliable multicast that just goes in a single step, that would be fantastic, but it's not the case, right? Well, you're not really trading off anything. So the number of steps it takes to disseminate the entire information is one trip up and one trip down, right? But keep in mind that the trips at the bottom, because you match perfectly, hopefully perfectly on the underlying networking, are going to be much faster than trips at the top. Then essentially the price you pay for the entire protocol is just the very top communication, right? So the building to global coordinators are going to be the ones that dominate, and that's essentially a price that you cannot avoid anyway, because somehow you have to convince somebody else in another data center to run. That was the goal of the entire exercise, right? I mean, if your entire system is a rack, then you're done and you're good. Now, this kind of a distinction between system, rack, room, data center, in between data centers, turns out to be crucial, and it's one of the primary concerns, for example, that engineers at Google have when they design their software. They try as much as possible to make the distinction between this, if you want, 4 slices of the hierarchy, right? So you need to run a very different program if you know you're going to communicate within the same rack versus a program that communicates within the data center. And that goes for reliability as well. And that also goes for things like how bounded the messages are. So it turns out that it's much easier to both detect failures and to make strong assumptions about how much time a certain operation should take if you in fact stay within a rack. So within a rack, things are going to be extremely reliable. I mean, look, there is the danger that the entire rack is inaccessible because the power went down, so it's not particularly fault tolerant. Well, it depends on what your expectations are, I guess, but, right? So you might have an issue with that because you're at the mercy of the same, let's say, power supply or whatnot. But when it comes to the activity that goes within a single rack, you're really not going to see that many failures in general. And the communication, for example, messages being lost because of the communication layer are almost unheard of. The probability that a single bit is flipped when you use modern switches is 10 to the minus 15. It's virtually not, you're not going to have a single bit flip in an entire year of communication, right? So things, in fact, are very reliable when you're talking about a single rack. Now, another thing I have to make you aware, especially in the context of all this fault tolerance and so on, you might get almost a sense of paranoia from the discussion in this class and the discussion you're going to see in the industry and so on, in which people say, yeah, but is it fault tolerance? And if it's not fault tolerance, we're going to freak out and so on and so forth, right? If the system is relatively reliable and you don't have those problems happening, you're better off by dialing in a very different kind of fault tolerance mechanism in which you have a more expensive mechanism, which you can in fact afford because it's going to kick in much rarer, right? So, for example, some of the work in distributed database systems tries to capitalize on the fact that in fact things are very reliable and in fact latencies are relatively small if you stay within the same, for example, the same rack. So, for example, they figured out that after months and months and months of deployment that they've never seen a single message that got delayed more than 50 milliseconds. No matter what, the message did not get delayed more than 50 milliseconds. And if that's true in the particular scenario you have, right? That can be exploited in a massive way. Because essentially, if you send a message and you're expecting some kind of an acknowledgement, if it doesn't arrive in 100 milliseconds, you just know it got lost and you send it again. And it's a very reliable way to say it got lost. But that really depends on the specific technological stack you have and how you put the systems together. Okay? So you cannot make that assumption in general, but you might be able to make it by just understanding how the system is put together, what's going on in there. Right? And things do get, by the way, more and more and more reliable, in fact. Okay? Okay. Now another notion, and this is very high-level notion, it was introduced by Ken Berman in his system ISIS. It's called virtual synchrony. So this is not really a truly synchronous system, but it's a system that looks synchronous because you have atomic multicast, right? And it's synchronous because if you want, the beat on which everybody works is the delivery of the atomic multicast messages, okay? Now you still need a mechanism to do atomic multicast. And by the way, the work of Ken Berman on ISIS led to a company which he founded when he was an assistant professor at Cornell. Then he sold the company to NASDAQ. And NASDAQ used the atomic multicast protocol as the basis for the trading system, right? And then NASDAQ, of course, made a lot of money with the trading system, right? These electronic exchanges, in fact, have a massive distributed system problem or a collection of distributed systems problems. And they, in fact, are manipulating enormous amounts of money. So when they have a failure, it costs them in the order of hundreds of millions of dollars, right? When they get sued for billions, right? So imagine that a bug in a system you design will cost your company hundreds of millions of dollars. I mean, you think twice before deploying that kind of stuff, right? As opposed to, yeah, whatever, it's a little quirk, kick it, and it's maybe going to run. Okay. Now, in virtual synchrony, you're very worried about the actual delivery all the way to the application. I made this distinction before. The fact that the networking layer gets the message, it's not good enough. You need some confirmation that the application actually got it, right? So this kind of atomic multicast refers to what's delivered to application, not what's delivered to the networking. Okay, and that becomes very important, right? So, of course, the question is, OK, fine. What if I can't deliver the message to all of them? Then, in fact, you have to abandon the multicast and make sure that everybody knows that the multicast got abandoned. So even if the message got received, if you don't know for sure it got received by all the participants, you have to send a special message around to say, discard the previous multicast because we cannot atomically guarantee that everybody got it. If you don't know for sure everybody got it, you have to abandon it so that nobody gets it. It's not that nobody got it delivered. It's no application gets it delivered to the application. Okay. All right. Now, another big issue is message ordering. Exactly like idempotent operations that you can apply multiple times, certain applications can allow reordering of messages. Certain applications can't tolerate reordering of the messages. Right. Now, in general, you can say, hey, just to be on the safe side, make sure my messages are ordered. But as it's always the case, by insisting on order, you're giving up some of the performance. Now, I want you to understand that we already have in-order delivery when we use TCP, but that only for point-to-point communication, right? So if my system communicates with your system through a single TCP IP connection, it's hardwired in the TCP IP protocol to deliver the messages in order, right? In particular, the protocol itself is going to keep track of through those sequence numbers, which is a very complicated issue because of security, right? You need cryptographically secure sequence numbers and stuff like that, okay? But through those sequences, it keeps track of specifically what messages it should have gotten, and if it's missing one message, it simply won't deliver the message all the way up. That means messages can get stalled in the network stack until the correct gaps are filled and the messages can be delivered in order. So when you combine message ordering with multicast, especially an atomic version of the multicast, you get the most powerful version of the multicast, which is totally ordered multicast. So total ordered multicast, we mentioned, we had this before, I even had a quiz question. Let me tell you again what it is a multicast in which, again, messages are either delivered to all participants or none of the participants, but they are also delivered in the same order, right? Now, it's not necessarily the case that the order is pre-specified, which of the possible orders, but they are delivered in the same order to all the participants. And that becomes crucial if you are, in fact, running transactions on multiple sites. Because depending on what the transaction does, by reordering the transaction. So when it comes to a single system, the transactional semantic allows you to run them in any order, and you don't promise any order for the running. But when you run on multiple systems, you have to run them in the same. I mean, it can be any of the orders, but it has to be the same across all the systems, because if you don't, they are still going to recover inconsistent states. Right? So think about the situation in which you say, subtract $10 from my account and take 10% of my account and move it to another account. I'm not saying that this is something people usually do, but I'm saying this is something that could happen. Depending on which one you do first, the amount of money left in the two accounts is different. Now, that's not a problem if you run on a single system, because you say, I never promised you I'm going to run them in a certain order on a single system. And that's part of what transactions are all about. That's one of the things they relax, right? But that has to be the case at multiple sites. So if you decide to run first, take $10 out and then the 10%, you have to do so on all the servers. Okay. Now, when it comes to promises you can make for message ordering, right? And that, by the way, it happens with the transactions. You can make some relaxations, what you could possibly give up. You basically have 4 distinct things you could do. You can invent maybe some intermediate ones, but these are 4 clear ones. The first one is always, don't bother, whatever. It's the whatever case, right? Unordered multicast. What happens, happens. Wash my hands of it. By the way, sometimes these things have a nice name called best effort. For example, UDP, it's best effort protocol. That means, look, I'll try to do something, but it doesn't happen, and it's not my problem. Okay, unordered multicast. The other one is FIFO order multicasts. Okay, the name is a little bit deceiving, but FIFO means in order. So why is it not total multicast? Well, it's in order, but only from the point of view of a single participant. So what that means is, if the message is produced by the same process, the sequence of messages coming from the same process show up in the order in which they were issued by that process at all sites. Now, there is no promise with respect to how messages from different sources interleave, and everything is allowed, right? Now, how do you enforce this, for example? You just put a sequence number. So whenever a single source produces the messages, you put a sequence number, you know if you have gaps, and you simply don't deliver the message if you have gaps. This is precisely what TCP does. In fact, if you use TCP connections, then you're essentially going to have in-order delivery. Okay? Good. FIFO. Ordered multicast. So as we go from the unordered to the bottom, the protocol becomes heavier and heavier and heavier, and things become nastier. Okay. So to do this, you just need some sort of a sequence numbers, which is a well-studied problem and implemented in TCP/IP. Then you have this causally ordered multicast, right? That means causality plays a role, and if there is any chance that the message is the cause of another message being received, you want to be sure that this order is actually preserved. One way to do that is through those vector clocks that we talked before, right? Now, you can use Lampert clocks, and that will do a relaxation, put more pressure on the system. Namely, if there is a causal relationship, they are definitely ordered in the correct way, but you might force an order when you don't need one. If you use vector clocks, then you force an order only when you need one, so potentially you will send less messages in the system at the expense of sending larger messages, okay, for the causally ordered multicast. And totally ordered multicast means on all the sites it goes in exactly the same way, okay? Now, if you could have a very fine-grained causality model and know for sure that certain messages cannot possibly interfere with other messages, right, then this could result in significantly less effort than totally ordered multicast. If you really go with a blank kind of situation, for example, if you don't know what's in the message and you just look at from where did you get the message, that everything looks dependent on everything, and you're essentially in a totally ordered multicast situation, right? So it depends on how much are you aware of what's in the message, which, by the way, it's a very tricky business, because for the most part, the payload, what the message carries, can be a very high-level issue that only the application understands, right? Different programming languages will have different encodings for various things. They usually agree on base data types, but even that is not completely true in Java, right? Because you're trying to be a little endian, big endian kind of aware. But, I mean, there are so many ways to pack into bits various things that you cannot expect the network card to understand. Now, there are some attempts to make the lower level protocols and the lower level systems be more aware of what's carried in the message and act upon such messages. And usually, this kind of technologies are called active something technology. You can talk about active networking, in which the network card understands some of the semantic of what goes on in there. Or even more importantly, active disks, for example. So just to give you an idea, for example, in a database system, I want to give you an idea of how much it helps to know what's in the message. In a database system, one operation you need to do quite often is filter. Give me only the tuples that match this predicate, right? But to some extent, you can think that, especially if you have a very selective predicate, that I ask the disk to give me the entire content just to throw most of it away. Now, if you have an active disk, you could essentially ask the disk controller, hey, give me only the things that have a chance to pass this predicate. And then you could cut down significantly the amount of communication that goes through. And this is a technique that can universally be used. Instead of asking a remote party, give me this entire thing, you could say, this is what I really want and give me only the subpart. Okay? When we talk about file systems, we can talk about to what extent it's possible to get only subparts. And the amount of cleverness you can do there is very large, as long as you understand a lot about what the application does. Now, this is a similar problem to the guessing and the kind of optimizations that goes on in the operating system. For example, if the operating system can guess what you're doing, it can do things in advance, mask latency, right? Or find ways to improve throughput. For example, it can use a certain kind of compression which might improve throughput, or as in the case for active disk, simply not transport things that are not needed, right? But this is kind of a tricky situation, because you now have to tie up low-level components with high-level components, and you have to agree on some sort of a communication protocol between the high level and the low level, or some representation, right? Because if the low level doesn't understand precisely the representation that the high level is putting in there, it might make mistakes, in which case you have to abandon it because you can't be sure that you carried out the correct operation, which is a bigger disaster than having some latencies in the system. Okay. All right, I think we already discussed about this. These are basically situations in which things are fine and things are not fine. I may not go through that. Right. So these are possible combinations that can actually be made with respect to what type of multicast you have, whether you have ordering or no ordering, and what kind of ordering you have, and when you achieve a total order delivery, right? I mean, it's basically just big words thrown in there to form all kinds of combinations. I don't think it's particularly important. The terminology is not even standard. I wanted to understand that, right? So, I mean, that's one of the tragedies of an area like distributed systems, right? You take one textbook, they call it one way. You go to Google and they say, well, we use a different textbook and we call it in a different way. And then you still need to sit down and see exactly what the definition says to figure out if we are talking about the same thing or not talking about the same thing. Right? Now, when it comes to virtual synchrony, we can discuss some interesting scenarios in there. And that will point out how fault tolerance can actually be enforced, detected, and all these things. Right? So, and this is the idea in ISIS. So the idea in ISIS is basically the following thing. You always have to make compromises like this. I can let messages float into the system, but I need to know which if you want, which messages are dirty and which messages are not dirty, and when to insist that things are pushed to the application, right? So whenever you talk about group membership, the question is who's in the group, right? The terminology in ISIS, in the paper of Ken Berman, is what's the view of the system. So the view is the collection of nodes that are active participants in the group. Okay? Now you allow members to join the group and members to leave the group, in which case you have to do a change of view. You had something similar but much more relaxed in the peer-to-peer system, in which more nodes were joining and leaving, and that was a big nuisance, right, to deal with that. That was part of the fun in there. So in some sense, it's very hard to have a global view in a peer-to-peer system because you have too many participants. And what you mostly cared about is the neighbors or potential neighbors of a node to know that that guy participates or doesn't participate. But in general, if you want to have just non-hierarchical simple group membership, this is what you would be worried about. So in this circumstance, one of the nodes, 4, detects that 7 is dead. Since 7 is dead, and you insist on having, I mean, you see, you cannot talk about reliable multicast of any sort if you don't agree who should receive the multicast. In this circumstance, we need to maintain an accurate description of who's in the group, because we need to keep track of the promise that we made with a reliable multicast, right? So we promised the message has to deliver either to all or none of the participants in the group, but then that means we have to agree on who's in the group. So 4 detects that 7 is faulty for whatever mechanism, right? Because it's faulty, it has to send to all the members of the group a view change message to say, hey, 7 is dead. We have to agree, all of us, that the group now does not include 7, because if you include 7, we bog down the entire protocol. Okay? Okay, that's fine. Now, what happens is the following. Everybody was in the process of sending all kinds of messages. And these are all multicast messages that had to be delivered. For some messages, you know for sure they got delivered on all sides, so safely could be sent to the application with with a atomic multicast. But some messages are so-called unstable messages, and they are simply, you're not sure if everybody got them. You can't deliver them to the application, so it's not clear what to do when a view change comes. So the protocol, and this is really the breakthrough in ISIS, the protocol in ISIS has to specify how you interleave these view changes and what do you do with the unstable messages, and what other messages do you need to make sure that you understand what the situation is. So the idea in ISIS was to, in fact, have some special kind of messages called flush messages. So before you, in fact, go ahead and do a view change, you have to make sure there are no unstable messages in the system. Because, you see, the trouble with unstable messages in the system is, OK, you promise you're either delivering them or not delivering them, but with respect to what group membership? You're about to change the group membership. So that's what prompted this entire situation. One of the nodes is faulty, so you have to change the group membership. So before you can safely change the group membership, in ISIS, you're going to send this flush message. So all the sides first, before you do the view change, will either abandon these unstable messages or deliver them, and only once that happens, you can actually switch to the new view. Okay? Which basically means if the view changes in the meantime, none of these views got propagated, and then you basically just get bogged down. Okay? Now, ISIS, in fact, is built on top of TCP, as most of the things out there. So you're not so much worried about the point-to-point reliability. It's ensured by TCP, and the point-to-point ordering, which again is ensured by TCP. Okay? And that helps in proving that a more relaxed version of the protocol is good enough. Right? So essentially some of these unstable messages eventually, so the flush message was, in this case, sent by 6. Right? Because it's the one that detected that the situation is needed. And eventually you get acknowledgments on the flush message, and you can actually go with a view change. And that's basically what's going to happen. Now, of course, the problem with these scenarios is other stuff can happen in the system as you go along, namely other guys die. So all these protocols have to take into account that the situation might have changed in the meantime, right? If another node dies, you already possibly started another protocol. So the protocol has to specify is, hey, if we distributed a view change, but we did not fully change because we had unstable messages, do we ignore or do we remember other messages that can come along, right? OK. Now, I still have about, how much time do I have? 7 minutes or 17? 7. So let me just plant the seeds for this. And then we're going to have the full discussion next time. So really the gold standard of activities you can do in a distributed system is a so-called, transactions, distributed transactions, which depend crucially on the notion of distributed commit. It's not never commit. It's either a distributed commit abort combination. Okay? So essentially, at the core of this is, how can we make sure that all the participants agree either that we go on and do something or we don't do the thing at all? The total multicast was kind of built in a little bit into this thing, but you can actually treat this problem as in fact, a separate issue. Okay? So 2 fundamental algorithms were proposed to deal with this idea of distributed commits. It's an all or nothing kind of semantic. The first one is called two-phase commit. And it turns out that two-phase commit has a rare but possible problem. And then the three-phase commit was proposed on top of that. What I really expected to get out of this class is to understand how two-phase commit works. Because it's really used, and it needs to be used at least every now and then to make some kind of global agreement between multiple sides. Okay? Now, all of these protocols are going to depend crucially on a coordinator. So remember, having a pin down in the system coordinator is bad, but having a coordinator per se is not bad, and it accelerates algorithms. So a potential technique that's used very often is to use some sort of a leader election protocol to vote who should be the coordinator, and then to go with the coordinator and detect a failure of the coordinator. Okay. So this two-phase commit, which I'm going to briefly describe now, depends on the idea of a global coordinator. Again, leader election algorithms can help you find such a thing and maintain or if not, Boole algorithm or some other algorithm to find another replacement, if you want, for the global. So when somebody has to initiate basically the commit, so it doesn't matter who starts first, but the action has to go to the global coordinator. So this two-phase commit will proceed in two phases. In the first phase, right, the coordinator will just send a message to all the participants to say, we need to commit. Right? All the participants have to send back an answer and to say whether they want to commit or abort. The coordinator then is going to look at how the voting goes and send the message. Now, here is the thing, and I want you to be aware of this. This is not only like multicast. Right? In the case of multicast, if somebody didn't get the message, you can send the message again. But when it comes to transactions, very tricky stuff can happen. Right? So it's not the case that if you send the same transaction to different systems, naturally they will all agree that they should commit or abort. You can abort for many, many different reasons. Right? So in particular, in this case, if any of the transactions for any reason decides to abort, everybody has to abort, because it's simply not possible to run the transaction. And it's not clear at all that reissuing the transaction will allow you to go over that abort. Right? So this is not a regular voting system. It's really, we all have to agree that we commit to commit, and anything else that happens, we have to abort. So again, in the first phase, in the first round, you essentially say, please send me whether you want to, please send me your vote, commit or abort. When the results come, if the coordinator gets any abort, we'll send everybody a message to say, let's all abort. Now, look, this protocol looks simple, but the big question, and we have to revisit this next time, is what happens in the presence of failures? Okay? And you can have all kinds of failures that can go wrong. In particular, there are two different types of failures you have to be worried about. A failure of one of the participants or a failure of the coordinator. Okay? So it turns out that two-phase commit, and I don't have too much time to go through all the details, we have to postpone it for Thursday, but two-phase commit has a problem with the failure in the coordinator. Because essentially, if you send the votes, if you don't send anything, then you can detect nothing got sent, and I mean, I'm ready to commit, why nobody bothers me to commit. But if the coordinator sends the request for votes and then dies, that creates a problem for the two-phase commit. So the death of a coordinator in between sending for votes, right, but then never sending the message back to say either abort or commit, these guys don't know what actually happened, and they deadlock in the situation. And three-phase commit, it's a variation of the protocol that adds more messages into the mix that, in fact, will take care of this situation. Okay? And we're going to see that next time because it requires very careful discussion. Okay? So essentially, what you're trying to achieve is to make sure that they all agree what the final state of the system should be. It's either the case commit, in which case all committed, abort, in which case all of them aborted, right? You might, and these are different phases in which you can be in it. You just start the entire computation, and ready, this is for the client, say, I'm ready to say yes or no for the entire protocol. Okay. All right. So let's revisit the two-phase commit and see a little bit the discussion about the three-phase commit next time. But this is, I mean, probably the kind of questions that pops up the most on any interview, right? That you say, oh, you took distributed systems, what's two-phase commit? It's kind of a given. It's like, two-phase commit. Okay? So do pay attention to what two-phase commit is and be able to answer questions about this. All right, so I'll see you Thursday. We continue the discussion. Hopefully we wrap up the entire discussion about fault tolerance and we can move to things like security and maybe a little bit of MapReduce and some other issues, distributed file systems, which are interesting in themselves.